Thank you for having me, and I'd like to give my special thanks to you all as a member of the Yonsei University. In this talk, I'd like to discuss about post-quantum cryptography and the role of the quantum computation. Actually, several years ago, my second boy showed this picture, and I asked, "What's that?" My second boy said, "This is universe strongest dragon grasshopper." So I asked, what does it mean? Strongest in the universe, and what's the dragon grasshopper? So he said that this is a dragon grasshopper, not the dragon, not the grasshopper. Yeah, and I believe that this is strongest in the universe. Yeah. Okay. So I will show this later again. Okay. Usually I start with in this usual talk. I always start with this statement. Always space theory defines or limits the ability of the information processing. The quantum information science is aiming at developing the faster, safer, and more precise information processing by changing the base theory from the classical to quantum theory. So everyone knows we use qubits, which can be superposed and entangled, and there are several candidate physical platforms to realize this qubit system and eventually to build a quantum computer. Actually, the best and simple way to explain why the quantum computer is powerful is quantum parallelism. For example, in the classical computation, we should identify the input and output one by one. But in the case of the quantum computing, we can use the superposition of the data, and we can process this superposed state at once. But actually, this is not 100% true, because if we should extract a real solution from this superposed state, we should perform the measurement, and then we can get one of them with a certain probability. So we should employ some efficient incorporating operations to improve the solution probability up to unity. Actually, that's the quantum algorithm. Then what's the algorithm? Actually, algorithm is a kind of a sequential set of commands for solving a problem. So the algorithm is a real-world terminology, but the algorithm become very important, especially in computer science. It's because the computer can express these states by using a simple 0 or 1 signals, and also possible to express this command operation with a fundamental set of logical gates. Here, I'd like to inform that the algorithms is not unique. So sometimes we meet the good algorithm, but sometimes we meet the poor algorithm. So the performance analysis is very important. For example, for the equivalent circuit, two circuits, we can directly see this looks better because it's simple with a few gates, and we can imagine that this circuit can generate the output very quickly because the gates, number of gates are small. But in the case of describing the problem hardness, we usually use the ratio or the rate of the increase in the number of gates to the increase in the problem size. For example, the increasing rate is exponential, then we say that this problem is difficult or intractable. But the increasing rate is polynomial, then we say that this problem is easy and tractable. So this is a computational complexity theory. So when we say the quantum computer is powerful, it means that we can solve a problem within the polynomial increase or the polynomial complexity, whereas there's no such a kind of algorithm in the classical computation. The dramatic example is factorization. Everyone knows that factorization can be solved with the polynomial time, whereas there's no such a kind of algorithm in the classical computation. Actually, the advent of this Schwarz algorithm, factorization algorithms, boosted the development of the quantum computing algorithms and other fields. And we also have the very famous quantum algorithm called the data search, which exhibit scalar to speed up. And another important quantum algorithm is quantum linear algorithm, often called the HHL, named after these inventors, the Harrow, Hassijm, and L.O.V.E. And this algorithm exhibit the exponential speed up compared to the classical diagonalization method. And this algorithm is special because this algorithm opens a new era and new phase of the quantum machine learning as a kernel of the quantum support vector machine. Okay, then this the celebrated quantum algorithms can be a threat to any crypto system, right? So we make this one solution. The first solution is use the quantum, which means that we can create a secure communication scheme and secure protocol by using the quantum principle. So it established very famous subfield like quantum secure communication and quantum key distributions and so on. Okay. Then second solution is to develop the crypto system based on much harder problem, even for the quantum computer. This is the post-quantum cryptography. Okay. Usually, cryptology consists of the two subfields, cryptography and cryptanalysis. Actually, PQC is quite closely related to the cryptanalysis because one of the main purposes of the PQC is to find a hard problem against the quantum computation. Okay, so there are some several candidate problems like this, but as I know, this full case can be solved for under some conditions within polynomial time, and even this isogenic-based problem can be solved, as I know, even with the classical computer by your notebook. Recently proved, as I know. So nowadays the strong candidate is a lattice-based problem, like shortest vector problem (SVP) or closest vector problem (CVP). But still, we don't know the exact hardness of this problem. Okay, I said one of the main purposes of the PQC is to investigate whether a given problem is hard or not against the quantum computation. So there is a very useful formalism called the hidden subgroup formalism. Okay, for example, let's consider factorization. This hidden subgroup is the natural number set. And we know that this factorization can have the polynomial solution in the quantum computation. Then for a given problem, suppose that you find its a hidden subgroup is the natural number, then it has been proved that for that problem, we can always find the quantum algorithm to solve that problem within the polynomial time. So what we should do for a given problem, what we should do is to find the hidden subgroup. Then we can evaluate its hardness by using the established table. Okay, it's very useful. So mathematicians is great. Yeah, so in the case of the SVP problem, we know that it's classified as a sub-exponential. But for a specific case, for example, in the ideal lattice, the SVP can be solved within the polynomial time. But in the worst case, still the SVP is a hard problem, exhibiting the sub-exponential complexity. Yeah, so the L.W.E, the learning with errors problem, L.W.E problem is one example of this the worst case SVP problem. Actually, this problem is very easy. Let's consider this linear function. Then the task is to find this, identify this function, namely finding this secret vector S for the given samples. We know that the linear problem can be solved easily, which means that we can solve this problem with only polynomial scale of the polynomial size of the samples. But here, if we assume the noise in this output, then this problem becomes intractable. And we call this problem the learning with error problem. So this problem can be considered as a strong candidate for the PQC crypto system. And recently, this problem it has been shown that this problem is as hard to solve as the several worst-case SVP problem. And the best classical algorithm exhibit this sub-exponential. Then really, is it impossible to solve this problem with quantum? Actually, several years ago, the two papers have been published. In these papers, the Cross and the Grillo, very clearly proved that this L.W.E problem can be solved within the polynomial time. Okay? But these two papers also have some caveat. Actually, hint is here in the title. Actually, in the title, exactly mean that learning with error problem can be easy. Can be easy. Yeah, when we can use this largely superposed quantum sample. Yeah. So very important thing is the data, actually data, the sample. So this, it means that this, the input sample consists of the very largely superposed classical data. So it's quite difficult to make this kind of prepare this kind of the state. Actually, we usually call this problem the QRAM problem. The QRAM is a quantum random access memory. And the second caveat is we should employ very heavy quantum operation like this. The quantum Fourier transform, like this. So several years ago, we considered some simple idea called known as the divide and conquer strategy, which is to divide the system into several fractions and apply the algorithm to the small size system. And here we proved that this strategy can be applied to the L.W.E problem, and we can enjoy the exponential speed up even with the small size of the superposition compared to the original Grillo's case. So we published paper, and also after that we also studied about the overall cost in terms of the FTQ, fault-tolerant quantum computation. Here we consider the overall cost. Here we employ the T-depth. The reason why we casted the T-depth is in the first fault-tolerant quantum computation, the T gate is the most expensive gate. So we usually employ this T-depth as the cost measure to evaluate this implementing circuit in the logical level. Okay, anyway, we investigated the overall cost of this the L.W.E algorithm, and we proved that even in this case we can reduce this overall cost down to the polynomial scale. Okay, and also we published the paper. Okay, and so many people asked me, so can they actually attack me? Not the problem. Can they break it or not? So I always answer, this question is wrong. Actually, this kind of the discussion always make a meaningless debate. So my answer is I'd like to emphasize that the quantum algorithm researchers should design and develop the quantum algorithm to attack this hard problem. And then the crypto people can use this result to enhance or develop the post-quantum cryptography system. So, and proper interplay between these two, attack and defense, can make the real the desirable crypto system. Otherwise, there is no quantum algorithm, no crypto analysis, then the PQC meet like this situation. The dragon, blah, blah. Yeah, which is created by just a belief, not a science. Okay, so summarizing, I'd like to emphasize more. So firstly, there is some overestimate vision about the quantum computer. For example, the quantum computer can solve everything very strong, but this is not true. And also there is some kind of deterministic claims about the PQC. For example, the quantum computer can never break the PQC. This is not also true. Okay, so I think there is a need for interactive research between these two fields, and we should discuss always. Okay, thank you.